Good morning to one and all. I am V. John Reddy, Assistant Professor in the Department of Physics from Nalla Narasimha Reddy Engineering College. Today we are going to discuss about the carrier concentration in intrinsic semiconductors. We know that in the intrinsic semiconductors, the charge carriers are electrons and holes. These electrons or holes are generated due to the breaking of covalent bonds. Okay, here the number of electrons equals to number of holes, and we know that the electrons are present in the conduction band and holes are present in valency band. Hole is nothing but the vacancy of electron is we are called the hole. Okay, here we are going to calculate the density of electrons in conduction band. Okay, now we are going to calculate the density of electrons. Here the number of electrons in the conduction band per unit volume is we are called the density of electrons, and that is represented by N. Okay, the number of electrons in the conduction band per unit volume is we are called the density of electrons, and that is represented by N. Here I am considering a small area, the small density dn be the number of electrons available between the energy intervals E and E plus dE. E and E plus dE in the conduction band. Okay, and that is we are taken. Here I am taking the energy level. This is a valency band and this is a conduction band, and the bottom of the conduction band is EC and top of the conduction band is infinity. Here the energy level E and this is a dE, and the number of electrons presented in between these two, E and E plus dE. Okay, that is we are taken dN. dN equals to Z of E dE into F of E, where Z of E dE is represents density of states. Okay, density of states means how many energy states presented in between these two, that is E and E plus dE. That is the density of states. The next F of E is represents the electron occupancy probability. Okay, in those energy levels how many electrons are occupied, that is represented by F of E, where F of E is a Fermi-Dirac distribution function. F of E is a Fermi-Dirac distribution function, and Z of E dE is the density of states. Okay, this is for a small area, that is dN, a small area. There is E plus E and E plus dE, dN. Suppose if you want to take complete the density of electrons in the conduction band, we need to take integration of this dN from the bottom to top of the conduction band. That is we are taking N equals to integration of EC, lower minimum energy is EC, that's why EC to infinity dN. This equals to EC to infinity, integration of EC to infinity dE FE Z of E F of E dE. Okay, from this one, from the density of states, we know that Z of E dE equals to 4 pi h cube by 2m whole to the power of 3 by 2 e to the power of 1 by 2 dE. Okay, but actually here the electron is m is the mass of the electron, but we know that here the electron is not in the rest position. The electron is having the two masses. One is the rest mass is different from the, and another one is if the electron is under the periodic potentials, the mass is variable. Okay, that's why that mass is we are called the effective mass of the electron. And this here in the above equation, m is replaced by the m star e. M star e is the effective mass of the electron. And here we have the energy E, but here the energy E, that energy is we are taken E minus EC, we minus the minimum energy. Here in the place of E, here we are taken E minus EC. Then Z of E dE equals to 4 pi by h cube into m star E whole to the power of 3 by 2 into E minus EC whole to the power of 1 by 2 dE. And the F of E from the Fermi-Dirac distribution function, F of E equals to 1 by 1 plus e to the power of E minus EF by kT. This can be written as 1 plus e to the power of E minus EF by kT whole to the power of minus 1, and then we can get E minus EF is very much greater than kT. F of E equals to, we can get e to the power of EF minus E by KT. This is equation 4. And substitute equation 3 and 4 in equation 2. Then we can get N equals to integration EC to infinity 4 pi by h cube 2 m star E whole to the power of 3 by 2 into E minus EC whole to the power of 1 by 2 into e to the power of EF minus E by KT into D. Okay, here this 4 pi by h cube m star E and this e to the power of EF by KT. These all are different terms. Okay, take outside from the integration. Then only the integration term part is integration EC to infinity E minus EC whole to the power of 1 by 2 into e to the power of minus E by KT d. To solve this integral part, let us consider E minus EC equals to x. Here I am considering E minus EC equals to x. Then E equals to, what is the E? E equals to EC plus x. Next differentiation, dE equals to dx. Okay. If E tends to EC, what happen? If E tends to EC, the lower limit will be changed from EC to 0. X tends to 0. If E tends to EC, x tends to 0. If E tends to infinity, x tends to infinity. That's why the limits are changed from EC to 0 and infinity to infinity. Then substitute these values in this one above equation. Then N equals to 4 pi by h cube into 2 m star E whole to the power of 3 by 2 into e to the power of EF by KT integration 0 to infinity x to the power of 1 by 2. To in the place of E, here we have the E. In the place of E, we write the EC plus x. Okay, here minus E. So my e to the power of minus EC by KT into e to the power of minus EX by KT dx. Okay, and take the out from the integral part, this e to the power of minus EC by KT. Then we have the integration 0 to infinity x to the power of 1 by 2 into e to the power of minus EX by KT dx. This integral part is solved by using the gamma function. This value is, we will get KT whole to the power of 3 by 2 into pi by 2 by 2. Pi whole to the power of 1 by 2 by 2. Okay, substitute this equation 6 in equation 5, then we can get N equals to 4 pi by h cube into 2 m star E whole to the power of 3 by 2 into e to the power of EF minus EC by KT into e to the power KT whole to the power of 3 by 2 into pi whole to the power of 1 by 2 by 2. By we are finally we will get 2 into 2 pi KT m star E by h square whole to the power of 3 by 2 into e to the power of EF minus EC by KT. This is the density of electrons in the conduction band. Okay, thank you.